I start each morning thinking about heat, not metaphorically, literally. The computer in front of me, the one processing these words as I write them, is warm to the touch. That warmth is not waste. It is not inefficiency waiting to be engineered away, it is payment. Every time a bit of information is erased inside that machine, energy must be dissipated as heat into the surrounding environment. This is Landauer's principle, discovered in 1961, and it sets a minimum thermodynamic cost for computation. At room temperature, erasing one bit requires at least kT times the natural logarithm of 2, about 3 times 10 to the minus 21st joules, to be released as heat. Your computer erases trillions of bits per second. The warmth you feel is the accumulated debt of all those erasures, paid in full, every microsecond, without exception. This is not a problem to be solved. This is the structure of reality. Information is physical. Changing information states has thermodynamic cost. The universe keeps accounts, and the second law of thermodynamics is the ledger. Now, imagine you want to build something that does not merely erase bits of information on a silicon chip. Imagine you want to dynamically reshape the geometry of space-time itself, to compress space in front of a vessel, expand it behind, create a bubble of flat space-time in between that can move faster than light without technically violating relativity. This is the Alcubierre warp drive, a legitimate solution to Einstein's field equations proposed in 1994. The standard objection is energy. You would need exotic matter with negative mass energy density, and you would need a lot of it. Early calculations suggested you would need the mass energy equivalent of the observable universe concentrated into negative form. Later refinements brought it down to perhaps the mass of Jupiter, then maybe just a few solar masses of exotic matter arranged in precisely the right configuration. Those numbers are so large, they feel like the end of the conversation. But they are not the problem, not the deepest problem. The deepest problem is that bending spacetime is an irreversible thermodynamic process. The spacetime metric, the mathematical object describing the geometry of space and time, is not an abstraction floating above physical reality. It is encoded in the quantum fields that permeate every point in space. When you change the metric, you are forcing those fields into new configurations, you are performing a computation on the quantum vacuum itself, and like every computational operation that changes state, it generates entropy, not as a side effect, as the central, unavoidable consequence of doing anything irreversible to a physical system. Let me show you what that means in practice. The Alcubierre metric describes a warp bubble with a characteristic radius, let us say 10 meters, roughly the size of a small spacecraft moving through space. To create this bubble, you must curve space-time severely at the bubble's boundary. The Wiki curvature tensor, which measures how space-time is being deformed, spikes at the walls of the bubble. Every time that curvature changes, every time the bubble accelerates, decelerates, or even maintains its shape, while moving through quantum field configurations that vary from point to point, the vacuum state is being disturbed. Virtual particle pairs that would normally annihilate before becoming real are being torn apart by the curvature gradients. Some become real particles, carrying away energy. This is the dynamical Casimir effect, closely related to Hawking radiation near black hole horizons. Except here, you are not orbiting a black hole, you are creating the horizon. The bubble wall itself acts as a boundary where the geometry changes so abruptly that the vacuum begins to radiate. The entropy generated by this process scales with the surface area of the bubble and the rate of curvature change. For a 10-meter radius bubble moving at substantial fractions of light speed, the entropy generation rate is not subtle. One careful analysis suggests that the effective temperature of the particle creation at the bubble wall, the temperature that an observer at the wall would measure via the Unruh effect, could reach millions of Kelvin or higher, depending on the acceleration profile, millions of Kelvin at the boundary of your spacecraft, not because you are running engines that produce heat as exhaust, because you are forcing space-time to change shape, and that operation has a heat signature that cannot be eliminated. Now here is where the numbers stop being abstract. That heat must go somewhere. Thermodynamics does not permit you to generate entropy and simply will it away. The entropy either radiates away as thermal photons and particles, or it accumulates locally, raising the temperature of the space-time region itself. Radiation obeys Stefan Boltzmann scaling. The power radiated goes as sigma times temperature to the fourth power times surface area, where sigma is the Stefan Boltzmann constant. For a macroscopic bubble with a large surface area, You can radiate significant power, but only if the temperature stays high enough, and only if that radiation can actually escape the region without interacting with the warp bubble geometry itself, which it cannot necessarily, because the bubble is precisely designed to distort the paths of light and energy. The very structure you are trying to maintain interferes with the primary mechanism for dissipating the entropy it generates. Meanwhile, the entropy generation rate from curvature dynamics scales differently. It scales with the volume of the distorted region, with the fourth power of the velocity as you approach light speed, and with the cube of the ratio between the bubble size and the Planck length. For any macroscopic bubble, anything larger than subatomic scales, this ratio is enormous. A 10-meter bubble is about 10 to the 36th power Planck lengths across. The entropy generation rate is catastrophic. It vastly exceeds the rate at which any known physical process could remove that entropy from the local spacetime region. What happens when entropy accumulates faster than it can be dissipated? The local temperature rises. The quantum fields become thermally excited. The stress energy tensor, the object that tells spacetime how to curve, begins to deviate from the configuration you need to maintain the warp bubble. This is called quantum back reaction. The vacuum you are trying to warp is fighting back, not with intention, but with statistical mechanics. The more entropy you generate, the more the actual stress energy of the fields deviates from the exotic matter distribution your warp drive requires. The bubble geometry becomes unstable, and because the instability itself generates more entropy turbulence in the fields, further particle creation, the process runs away. The timescale for this runaway collapse depends on the specifics, but it is not measured in years or even seconds. For a macroscopic bubble attempting to move at relativistic speeds, the collapse timescale could be microseconds or less. The bubble does not fail because you run out of exotic matter, it fails because it cooks itself. You might think, then radiate the entropy more efficiently, use the bubble's own geometry to channel it away, or dump it into extra dimensions if they exist, or find some other clever mechanism. But every mechanism you invent to remove entropy is itself a thermodynamic process. If you build radiators, they generate entropy in their operation. If you try to channel heat through exotic field configurations, those configurations must be maintained, and maintaining them against thermal fluctuations costs energy and generates entropy. If you propose dumping entropy into extra dimensions, you must open a coupling between our four-dimensional spacetime and those extra dimensions, and that coupling, if it is strong enough to matter, will itself become a source of particle creation and entropy generation. You cannot win this game. The second law does not negotiate. There is a deeper reason, and it returns to where we started, information. The metric tensor at every point in spacetime encodes information about the geometry at that point. When you change the metric dynamically, you are erasing the previous geometric information and writing new information. Landauer's principle applies. Each bit of geometric information that is erased must dissipate kT times the natural logarithm of 2 of energy. Now consider how many bits are involved. Spacetime is not discrete at scales we can access. It is a continuum, at least down to the Planck scale, but we can estimate. If we discretize spacetime at, say, the Compton wavelength of an electron, roughly 10 to the minus 12 meters, the number of points in a 10-meter bubble is approximately 10 to the 39th power. At each point, the metric tensor has 10 independent components. The total information content is staggering. And you are not changing it once, you are changing it continuously at whatever rate is necessary to maintain your bubble while moving through space filled with varying quantum field configurations. The integrated information erasure cost the total entropy generated is not a small correction, it is the dominant term. This is what I mean when I say thermodynamically suicidal. The warp drive does not fail because we cannot imagine exotic matter into existence. It fails because the act of warping spacetime is a kind of computation performed on physical reality, and that computation has a heat cost that scales catastrophically with size and speed. The bubble collapses under its own entropic burden before it can go anywhere. Not because the engineering is difficult, because the second law forbids it. You might ask whether this applies to all possible warp drive geometries or only to the Alcubierre metric specifically. The answer is all of them. Any configuration that achieves faster than light effective travel by warping spacetime must create regions of severe curvature somewhere. Those regions generate entropy through the mechanisms I have described. The more you try to smooth out the curvature to reduce entropy generation, the larger the bubble must become to achieve the same effective velocity, and the larger bubble encloses more volume, more field degrees of freedom, more information that must be continuously updated, you can shift the problem around, you cannot eliminate it. Some researchers have proposed warp drive variants that avoid horizons, or that use different shape functions, or that remain subluminal and use spacetime warping only for propulsion assist. These might avoid some of the worst runaway instabilities, but they do not avoid the fundamental entropy cost. They merely reduce it to a level where collapse takes minutes instead of microseconds. For interstellar travel, minutes are not enough. Let me make this concrete with a specific failure mode that reveals why no geometric cleverness can save you. Suppose you attempt the most conservative possible warp drive. Subluminal, modest curvature, a bubble that contracts and expands gently rather than maintaining a shock from geometry. You are traveling at, say, 1/10 the speed of light fast by human standards, but well below relativistic regimes where the worst entropy scaling appears. The curvature at your bubble boundary is smoothed out over a transition region several meters thick instead of a sharp discontinuity. You think perhaps this configuration is thermodynamically viable. Calculate the entropy generation even for this gentle case. The transition region still exhibits time-varying curvature as the bubble moves through quantum vacuum fluctuations that are never perfectly uniform. The Ricci scalar, a measure of total curvature, oscillates. Each oscillation corresponds to the vacuum fields being pushed into excited states and then relaxing. But relaxation is never perfect. Some excitation energy converts to real particles that escape the region. Over the hours or days of travel required to reach even nearby solar system destinations at this speed, the accumulated entropy becomes substantial. The particles you have created carry momentum. That momentum must be balanced by momentum changes in your bubble. The bubble drifts, its shape distorts slightly, and those distortions propagate as gravitational waves that carry away more energy and generate more entropy. Now you must actively maintain the bubble shape against these perturbations. Active maintenance means sensors, feedback systems, exotic matter configurations that respond dynamically to keep the geometry stable. But each feedback operation has thermodynamic cost. The sensors must collect information about the local field state, that is a measurement, which by quantum mechanics disturbs the system and generates entropy. The feedback system must compute the appropriate response, that is information processing, which generates entropy through Landauer's principle. The exotic matter must be manipulated, moving it, changing its density distribution, all of which are irreversible mechanical processes that generate entropy. You have replaced the natural collapse with a control system that generates entropy even faster through the effort of maintaining control. The gentle warp drive buys you more time before collapse, but it does not avoid collapse. It merely changes microseconds to minutes, and minutes are not enough. There is something else that happens at longer timescales which makes the problem worse rather than better. Thermal noise. At any finite temperature, the quantum fields exhibit random fluctuations. These fluctuations interact with your bubble geometry. Most of them are small, they push the bubble wall by nanometers, they create tiny ripples in the curvature that damp out quickly. But fluctuations follow statistical distributions. Occasionally, a large fluctuation occurs. In a stable system, large fluctuations are rare enough that the system recovers before the next one arrives. But your warp bubble is not stable, it is metastable at best, held in configuration only by continuous entropy generation and dissipation. When a large thermal fluctuation hits, it drives the system further from its target configuration. The feedback systems must work harder to restore order. They generate more entropy. The local temperature rises slightly. Higher temperature means larger and more frequent thermal fluctuations. The cycle accelerates. This is thermal runaway, and it is a generic feature of any system that must continuously expend energy to maintain order against a thermodynamic gradient. Your warp drive is precisely such a system. The collapse may be delayed, but it becomes inevitable not as a possibility, but as a statistical certainty. Now consider what you might try next. Perhaps instead of maintaining one continuous bubble, you pulse the warp field, turn it on for brief intervals, let the entropy dissipate, turn it on again. This is a reasonable strategy for many thermodynamic systems. Heat engines use cycles for exactly this reason, but a pulsed warp drive presents new problems. Each time you turn the field on, you must create the curvature distribution from scratch. Creation costs entropy. You are changing the metric from flat to curved, which is an irreversible operation. Each time you turn the field off, you must let it collapse back to flat. Collapse costs entropy. The curvature does not simply vanish, it radiates away as gravitational waves and particle creation, both of which carry entropy. The pulsing strategy does not reduce the total entropy cost. It distributes it across multiple creation and destruction events, each of which has startup costs and shutdown costs that add to the total rather than reducing it. And during the off phases, you are not moving faster than light, you are coasting, the average velocity is reduced. To achieve the same journey time, you must pulse at higher frequencies or create stronger curvature during the on phases. Both options increase the entropy generation rate. You are back where you started, only with added complexity. What if you abandon the bubble geometry entirely and pursue a different approach, wormholes, for instance? Traversable wormholes also require exotic matter, but they are static solutions rather than dynamic ones. Perhaps a static geometry avoids the entropy generation problem. This hope does not survive contact with the details. To create a wormhole, you must assemble exotic matter in a specific configuration. The assembly process is dynamic. It costs entropy. Once assembled, the wormhole throat must be held open against quantum fluctuations that constantly try to pinch it closed. Holding it open requires continuous expenditure of energy, which means continuous entropy generation. And if you want to send something through the wormhole, a spacecraft, a signal, even a single photon that something carries energy and momentum that perturb the throat geometry, the perturbations must be corrected or the throat becomes unstable. Correction costs entropy. The wormhole is not an escape from thermodynamic constraints. It is another system that must pay the entropy tax continuously to avoid collapse. You begin to see the pattern. Every method for circumventing the light speed barrier through spacetime manipulation encounters the same fundamental obstacle. Changing spacetime geometry is equivalent to processing information in the quantum fields that encode that geometry, and information processing has unavoidable thermodynamic costs. Those costs scale with the size of the region being manipulated, the speed at which it is manipulated, and the severity of the curvature being created. For macroscopic regions, fast manipulation, and severe curvature, all of which are necessary for any useful faster-than-light travel, the costs become prohibitive, not in the engineering sense, but in the thermodynamic sense. The universe does not have enough entropy absorption capacity in the relevant spacetime volume to accommodate what you are trying to do. The system collapses under its own entropic weight. There is a second place where the argument appears to soften and instead becomes total. Perhaps you think future physics will reveal that spacetime is not fundamental. Perhaps it is emergent from some deeper substrate entanglement patterns in a holographic boundary theory, or discrete graph structures in loop quantum gravity, or something else entirely. If spacetime emerges, maybe we can manipulate the underlying degrees of freedom directly and avoid the thermodynamic costs of manipulating the emergent geometry. But this does not help. If spacetime is emergent, then the entropy we calculate is not an artifact of choosing the wrong variables, it is the entropy of the fundamental degrees of freedom themselves. Changing the entanglement structure that gives rise to spacetime geometry is still an irreversible process. It still generates entropy. Landauer's principle does not care what ontological level you apply it at. Information is physical wherever it lives. In fact, the holographic principle makes the problem worse, not better. If spacetime geometry is encoded on a lower dimensional boundary, then the maximum entropy a spatial region can contain is proportional to its surface area, not its volume. This is the Bekenstein bound. For a warp bubble, the relevant surface is the bubble boundary. The maximum entropy scales with the area of that surface times the cube of light speed divided by 4 times the gravitational constant times Planck's constant. For a 10-meter bubble, this maximum entropy is about 10 to the 69th power times Boltzmann's constant. That sounds like plenty of headroom until you calculate the rate at which you are generating entropy. The entropy generation per unit time for a relativistic bubble can approach 10 to the 60th power entropy units per second. You have microseconds before you hit the holographic bound, at which point the region develops a trapped surface and you have created a black hole, not a warp drive. The universe enforces its bookkeeping with horizons. What about quantum error correction? Information theory has shown that certain quantum states can be protected from decoherence through clever encoding. Perhaps the warp bubble geometry could be encoded in a quantum error correcting code, allowing the configuration to be maintained without continuous entropy generation. This is a beautiful idea. It does not work. Quantum error correction requires measuring syndrome bits and applying corrective operations. Those operations are themselves physical processes. They cost energy, they generate entropy, and critically, they cannot correct continuous variable errors like the position of a curvature field with perfect fidelity. The no-cloning theorem forbids it, residual errors accumulate. Over macroscopic scales and macroscopic times, the error accumulation becomes the dominant source of entropy generation. You are back where you started, only now you have added the entropy cost of running the error correction protocol on top of everything else. Let me be precise about what this means for the dream of faster-than-light travel. It means the barrier is not technological. It is not that we need better materials, or more energy, or a deeper understanding of quantum gravity, though all of those might be true as well. The barrier is that the universe treats information as a conserved, accountable quantity with thermodynamic weight. Every time you change the state of a physical system irreversibly, you pay a heat cost. Space-time geometry is a physical system. Changing it irreversibly generates entropy. For macroscopic changes happening quickly, which is what any useful warp drive requires, the entropy generation rate exceeds the maximum dissipation rate by orders of magnitude. The bubble collapses. Always. Everywhere. Not because we have not tried hard enough, because the second law of thermodynamics is not a suggestion. This is the quality of impossibility I want you to feel. Not we do not know how yet, not the engineering is prohibitively difficult, but something closer to the universe has already answered, and the answer is written in the structure of irreversibility itself. The same laws that make computation possible, that allow information to be stable, that permit memory and causality and the forward flow of time, those same laws forbid the kind of macroscopic space-time manipulation that would let us slide past the light speed limit without paying the debt in full. And here is the turn I did not expect when I first started working through these calculations. The impossibility is not arbitrary. It is not the universe being needlessly restrictive. The thermodynamic constraints that kill the warp drive are the same constraints that make the universe habitable. If space-time could be warped without entropy cost, it could be warped by any sufficiently energetic process. Supernovae would create warp bubbles, neutron-star collisions would tear space-time into topological chaos, the vacuum would be unstable against runaway curvature fluctuations fed by quantum noise. The reason we live in a universe with stable matter, persistent structure, and causal order is precisely because changing geometry is thermodynamically expensive. The barrier to the warp drive is the foundation of everything else. You are left, then, with a choice about how to hold this. You can mourn the closure of a particular dream, the dream of stepping across light years in moments of touching distant worlds within a human lifetime. That mourning is real, and I do not dismiss it. Or you can sit inside the recognition that some constraints are not failures of imagination, but signatures of deeper order. The universe keeps books. It tracks every bit of information, every irreversible change, every increment of entropy. That bookkeeping is what prevents chaos. It is what allows stars to burn steadily for billions of years, what allows chemistry to be reproducible, what allows neurons to store memories and retrieve them later. The same law that says your warp drive will collapse in microseconds is the law that says your thoughts will still be yours tomorrow. I do not know how to reconcile the loss and the gratitude. I know only that the barrier is real, and that it is not going anywhere, and that calling it thermodynamically suicidal is not rhetorical flourish. It is precise. The warp drive doesn't fail because someone shoots it down. It fails because it devours itself, because the entropy it generates in the act of existing exceeds the entropy the surrounding space-time can absorb, because the second law is not interested in our dreams. It is interested only in whether the accounts balance, and for the warp drive, they do not. They cannot, they never will. That is the answer, not the one we wanted, but the one the universe has been giving us all along, in every bit of heat our computers exhale, in every irreversible moment that becomes the past. The cost of changing reality is paid in entropy, and some changes cost more than the universe is willing to charge.